guys, this is Sakshi and I welcome you all to my EduTech platform, Way to Learn. So today's session is Let's Solve Together PYQs of Classical Mechanics. So from Classical Mechanics, it's from December 2011 paper. So let us see 3.5 marks and 5 marks problem. So let us start our problem session. So just have a notebook and a pen with you and try solving along with me. So this is why the session is named Let's Solve Together. So yes, the first problem is having a double pendulum, and we have to find the kinetic energy of this pendulum. So I have drawn the same diagram over here. So we have two masses M and M over here. Both have the same mass, and obviously this mass will have the coordinates x1, y1, and this mass will have the coordinates x2, y2. So we know that the kinetic energy is written as T is equal to half M x1 dot square plus y1 dot square plus half M x2 dot square plus y2 dot square. So we have to find x1 dot, y1 dot, x2 dot and y2 dot. So from this first coordinate, my x1 will be L sine theta 1. So x1 dot will be L cos theta 1 dot. And y1 will be L cos theta 1. y1 dot will be minus L sine theta 1 dot. Similarly here x2 will be L sine theta 1 plus L sine theta 2 and x2 dot will be L cos theta 1 dot plus L sine theta 2 dot, and y1 will be L cos, sorry, it's y2 will be L cos theta 1 plus L cos theta 2, and y2 dot will be L cos, sorry, it's differentiation minus L sine theta 1 dot minus L sine theta 2 dot. I have made a mistake over here, which is L cos theta 2 dot. Okay, so next we have to just directly substitute in our kinetic energy. So before that, we can just simplify by squaring all dot terms. So let me square the dot terms over here. So my x1 dot square will be L square theta 1 dot square cos square theta 1. y1 dot square will be L square theta 1 dot square sine square theta 1. Similarly, x2 dot square will be, you're going to square the whole, that is a plus b the whole square, you're going to perform that. So on doing that, you get okay. So similarly, y2 dot square will be, so here again we are going to perform a plus b the whole square. You are going to consider a as minus L theta 1 dot sine theta 1 and b as minus L theta 2 dot sine theta 2. So on doing that, you're going to get the same thing, which is So now we are going to substitute in our kinetic energy, which is T is equal to half m x1 dot square plus y1 dot square plus x2 dot square plus y2 dot square. So if you see over here, x1 dot square and y1 dot square, when you add these both, your cos square theta plus sin square theta will be 1. So your T will have now L square theta 1 dot square. Similarly, when adding x2 dot square plus y2 dot square, you'll have 2 cos square theta 1 and cos square theta 2 terms. So on doing that, you're going to get L square theta 1 dot square plus L square theta 2 dot square. And now we have this cos theta 1 cos theta 2 plus sin theta 1 sin theta 2. So that is written as cos theta 1 minus theta 2, because cos A minus B is equal to cos A cos B plus sin A sin B. So I am using that identity and I have simplified this. So our T will be written as half m L square into 2 theta 1 dot square plus theta 2 dot square plus 2 theta 1 dot theta 2 dot cos theta 1 minus theta 2. So which is option B. So I hope you understand this problem. So let us see our problem 2, which is from special theory of relativity. So here a constant force F is applied to a relativistic particle of rest mass m. So if the particle starts from rest at t is equal to 0, its speed after time t is what? So we have to find the speed, right, which is v. So we know that F is equal to, we have been given that a constant force is applied. So according to Newton's law, F will be is equal to dp by dt. So I can write this as dp is equal to f dt ft plus c, constant, integration constant. So I know that at time t is equal to 0, my momentum will be 0 because the particle is at rest, so there is no motion, hence my momentum will be 0. So my c will be 0. Now you can write this as fp is equal to ft. Okay. Now what do we know? That this is a relativistic particle. And I also know that p is equal to mv. So since it is a relativistic particle, I can write this as m divided by root over 1 minus v square by c square into v. Right? And similarly, I can equate this to ft. So now performing simple mathematics, on performing a simple mathematics step, like you have to just take this over here. I'll just do few steps. So I need v, that is speed. So I'm going to take all the v terms to one side. So now here v square will be f square t square c square divided by m square c square plus f square t square. So at last your speed will be ftc divided by root over plus m square. So this is a very simple problem. You just have to think what is the force and what can you give in the formula, like F is equal to dp by dt, and you know that this is a relativistic particle, and you can directly substitute your relativistic momentum and then just solve. This is just a simple problem, and you can see that it's option D. So you can gain easily 3.5 marks in this problem. So next, let us see our third problem, which is from stability analysis. So here you have to find the value of the value of the potential at equilibrium separation. So you have been given V of R to be minus A by R power 6 plus B by R power 12. So for the equilibrium point, you are going to do dou V by dou R equal to 0. So on doing that, I get so this is my equilibrium point. Now I have to find my potential at this equilibrium point. So I'm just going to directly substitute this R value in my potential, which is minus A by 2B by A plus. So you get the potential to be on taking LCM and finding out, you get the potential to be V of R is equal to minus A square by 4B, which is your option D. So you can see that from June 2011 and December 2011, we have a question from stability analysis. So let us see our next problem, which is from central force problems. So we have been given our potential, and L1 by L2 is given as 2. Now we have to find the value of R1 by R2. So what do? We have our potential, so we can use our V effective formula. So V effective is given as L square by 2m R square plus V of R. Here V of R is half K R square. So I know that dou V effective by dou R should be equal to 0. So when I do that, I get so L is equal to R square root over MK. So we have L1 and L2. So I can write my L1 as R1 square root over MK and L2 as R2 square root over MK. So I know that L1 by L2 is 2. And using this relation, I can write this as R1 square root over MK divided by R2 square root over MK. This is also going to be 2. So on doing that, I get R1 square by R2 square to be 2, and R1 by R2 will be root 2. So we have been asked the ratio of R1 and R2, and that is root 2, which is option A. So this is an easy 3.5 marks gaining question. Okay, so let us see our next problem. This is from 5 marks, and this is a very easy simple question. So we have to find the Lagrangian over here, and we have a particle of mass which is moving inside a ball, and the equation is given over here. Okay, so now we know that L is equal to T minus V, and T can be written as half m x dot square plus y dot square plus z dot square, and V is written as mg z because we have the equation with respect to z. So V is mg z. Now, and z is given as half a into x square plus y square. Now we are using our cylindrical coordinates. If you haven't seen my video for Lagrangian dynamics, you can just check my classical mechanics playlist. I have given how to solve a Lagrangian question, the steps. So I had been told that uh, if you have a Cartesian coordinate, then you have to convert them into a suitable coordinate system. So here I'm going to use cylindrical coordinate system. So I can write and okay, just let me explain this first. So on using the cylindrical coordinate, I get x is equal to r cos phi. I can write cos theta also, but if you see here the options, you're having phi term, right? So I'm going to use phi over here. So r cos phi and y will be r sin phi, right? And z will be given as half into a into, so I can write my z as half a r square, right? So now I have to find x dot, y dot and z dot in order to get my Lagrangian. So over here, my x dot will be, now see you have two variables. One is r and another is phi. So you are going to use UV formula. So I am going to use that and you get as follows. Minus. And similarly y dot will be and my z dot will be um, a r dot. So before substituting, we can just find x square, x dot square, y dot square, and z dot square term. So I'm going to do it over here. So my x dot square will be sorry for the handwriting. Similarly, your y dot square will be and z dot square will be a square r dot square. So when you add this x dot square, y dot square, and z dot square, you can see that these two terms cancel each other. And here you have cos square phi and sin square phi, which will add up and give you 1. Similarly, this term will also give you 1. So now if I write my T, kinetic energy, I will get half m r dot square plus r square phi dot square plus a square r dot square. And similarly, my v is mgz. So I have found z in terms of our cylindrical coordinates. So my v will be mga r square by 2. So L will be equal to T minus V. So I am going to get my L as half M into R dot square plus R square phi dot square plus A square R dot square minus GAR square. So in order to get the same answer as in my options, I'm going to write my L as half m 1 plus a square r square into r dot square plus r square phi dot square minus g a r square. This is my Lagrangian, which is equal to my option D. So this is an easy 5-mark question. Let us see our next question, and this is from again central force problem. So we have to find the total energy of the planet which moves in the inverse square central force field of the sun. Okay, so the mass of the sun is m, and we will consider the mass of the planet as small m. So we have to find the total energy. So we can basically write the energy as half mv square plus minus gmm by r. Right. So this will be as half mv square minus gmm by r. One is the greater m and capital M, and other is the small m. Okay. So this is my energy, and according to, okay, I can also write my L as mv r. Right. Okay. Now we are going to use the conservation laws. So first, according to energy conservation, I can write that energy at point A will be equal to the energy at point B. So EA should be equal to EB. So when I do that, I can write this as half mva square minus gmm by, here the radius is A, and at point B the radius will be B, should be equal to m square. This is my first equation from conservation of energy. Similarly, from conservation of angular momentum, I can write mva a is equal to mvb b. So I get vb to be va into a by b. So now my basic idea is to substitute this equation 2 in equation 1. So when I do this, I'll be getting half mva square, and I'm going to get my kinetic energy terms on the one side and the potential energy terms on the other side. So on doing that, I get minus half m va square by b square, which is equal to gmm by a minus gmm by b. So the next step will be, this is basic mathematics to solve all these steps. So if you don't get this, just try it on your own. Practice more, you're going to get this. Okay. I can cancel this BB over here, and I'm not going to cancel this half mv square, that is half mv square term. I'm just going to keep this as it is. So I can write this as let's see. So I get this half mv square term as gmm b by a into 1 by b plus a. So now I need to find the total energy. So I'm going to substitute in this equation. And instead of half mv square, I am going to substitute what we have got now. So my total energy will be uh, so on simplifying this, you're going to get the total energy as E is equal to minus G mm by A plus B. So which is option A. So now this is like we have solved detailedly, right? In detailed manner. But now I'm just going to give you two formulas for any questions where you can find the total energy and the angular momentum. So for an elliptical orbit, you can write this if you want to find the total energy, it is given as E is equal to G mm by A plus B, and the angular momentum is given as M into A plus B. So just note that total energy E and L are same at all the points. So even if your question is tricky to and they ask you a question like find the energy at this point or angular momentum at this point, they all are the same at all the points for an elliptical orbit. So you can directly use this formula, and instead of your given radius, instead of A and B, you can just substitute your given radius. And instead of mass of planet and mass of sun, you can substitute as m and m given. So I hope this is very useful for you. So let us see our next problem, which is from moment of inertia. So here we have a ring, okay, and we have to find the principal moment of inertia along the axis of symmetry perpendicular to the plane of the annulus. So here is the annulus, and we have radius A and B, and we have to find this moment of inertia. So basically, how do we solve such kind of problems? So we have to write this moment of inertia I. Okay, so just a second. I is equal to integral r square dm. So whenever you have to find the perpendicular, uh, okay, perpendicular to the plane of your given object, whether it is an annulus or a circular wire or anything, you're going to use this first formula I is equal to r square dm, integral of r square dm. So now how to find this? What is this dm? So this dm is given as mass by area into dA. So here, mass by area. If you have like this is a plane. If you see in the question, okay, we have to find which is perpendicular to the plane of the annulus. So in order to find the plane, like find dm, and given the question has plane, then we are going to use the area. If you have like you have to given, okay, if your question is given like find the volume or the length of the wire, then you'll be using accordingly. You can just put mass by volume into dv or mass by length into dx. So it is based on your question that you have to substitute over here. So here your mass will be m divided by a into dA. So on doing that, I get my I to be r square m by a dA. Now we know that density is equal to mass by volume, but surface density will be mass by area. So my surface density, I am going to consider it as mass by area, that is rho. So instead of m by a, I am going to use rho. So I here is given as r square rho, and instead of dA, I can use 2 pi r dr. So this is integral over a to b. So now on doing this, you're going to get so on integrating, you get I as so this is your uh, moment of inertia. But if you see the question, you don't have any density term over here. You have everything in terms of mass. So now I have to replace my density. So basically, if you see, I have told that rho is equal to mass by area. So this area corresponds to this part. So how can I find this area? This area is basically written as m divided by, this area is basically written as, this is a circle, right? So I can use pi r square. So that particular area can be found using pi b square minus a square. So I am going to substitute this term in my moment of inertia. So my I will be pi by 2 into m divided by b square minus a square, and this is simplified as, so now the moment of inertia is I is equal to m pi by 2 b square plus a square. So this is a standard equation. You can use this equation if you have a similar type of question, and when your radius is different. So you can use this b and a with your different radius given. So let us see our last problem, which is again from 5 mark, and this is from phase space dynamics. So I told that we need a potential to solve a phase space trajectory, right? So here we don't have any information about the potential, but using this information we can directly find which is suitable diagram for the given information. So if you see it's a ZPZ plane and the ball is bouncing perfectly elastically. So if you see the word perfectly elastically, so elastic means if it is going at a particular height, then it will come down the same, it will bounce back at the same height. That is, if my ball goes up to this particular height, then it will come back to the same particular height. Okay. And the question says that it is bouncing at a surface at z is equal to 0. So where does it bounce at? Z is equal to 0. So at z is equal to 0 point, my ball will bounce at a higher, it will bounce at a particular height, h. So when it bounces, its momentum will be maximum, right? And now I told that it is bouncing elastically, then it will come to the same height below. So if you see here, the momentum will be the minimum, right? So if you see the diagram, the ball bounces at z is equal to 0, so there is nothing over here. And whenever it bounces at z is equal to 0, the momentum will be maximum. Let me see, this is my momentum. And it will come down at the same height, which is over here. So the momentum will be minimum, that is, it will be minus pz. And similarly, if it bounces again to some height like this, then elastically it will come down to this height. Similarly over here. So when I draw, I get like this. So, which is similar to my option A. So this is an easy thing which you can just practically think this situation and draw that piece trajectory. So I hope you like this video. So thank you everyone. Like my videos, share my videos, subscribe my channel, and also hit the bell. And yes, remember everything to note down and practice along with me. So this was the session on Let's Solve Together. So see you tomorrow. Ta-da!